Before starting that, actually, I want to know how many people here knows about PostgreSQL. So everybody knows about PostgreSQL, and how many people worked on PostgreSQL, already work on PostgreSQL. So we have plenty of here. So here my name is Ibrar Ahmed, and I am a senior database architect at Percona. Percona is a performance consultant company, so I'm here to present the topic deep dive in PostgreSQL indexes. So we'll learn about the PostgreSQL indexes. In generally, I will start from the definition and the concept of indexes, how it works, and especially how it works in PostgreSQL. So topic will be the indexes, but we will target the PostgreSQL, how indexes in PostgreSQL works, how we create them, how it's actually implemented in PostgreSQL, and the concept, not the coding. We will discuss the concept of PostgreSQL indexes. So heap, and there is a concept in PostgreSQL, there is called heap and indexes. So I will give you an example. Take a book as a heap, right? Everybody reads the book. So if take that book as a heap. So when you start reading the book, you start reading each and every page of the book. But at last, when you want to see something in the book, what you do? You go to end of the page, book, and you can see the index. In that index, you search something, and you will get a pointer of that. What is the pointer of that? Pointer is the page number of that book. So you directly go to that page number, and you will find your desired result. That's the index. So what is heap? Heap is the book. And what is index? Index is at the end of the index where you find your data and the pointer of that data. That means the page number of that data. So keep in mind, whenever I say heap, it's actual data in PostgreSQL. When I say index, then it's index data. So in PostgreSQL, when we data store in tables, we call it the saved in the heap. So actual data, whenever store data, it goes to the table, and I will say that to heap. So rows, when I say rows, it can be, we can say that the tuples are rows. So they both are the same thing, stored in the table. Like when you save the data, insert the data into the table, that rows and tuples stored in the table. And every table in PostgreSQL has a physical disk or disk files, right? When you create a table, PostgreSQL creates a file for that table, a physical file for the table. It can be one or many. I will discuss that when it's many because of the size limitation. Because it's more than 1 GB, then it will create the multiple files of that. But at least it creates a one file for you. Then we will see where this file stored and how this actual data stored in the file. We create a table, create table foo, and that we have a 2 column in that. It's one is an ID and the second one is the name. And you see, there is a rel file node in PostgreSQL catalog table. PG class is a catalog table where you can select rel file node from PG class where rel name like foo. So rel name column is the name of the table. Okay. So PG class is a system table or catalog table, and you see this one 16384. What is this? Actually, this is the file name physical stored in the is a table file name. If you go, you can see that file physically on your disk. And this file is attached to the table foo we have created already. So you can go here and then you can see where this file stored. PG data. The PostgreSQL, it is a directory where PostgreSQL clustered or tables or databases are stored. So in that directory you can see that file. Sorry. You can see this file. This is the PG data, actual cluster directory, and this is the base, and this is the database name, and this is the actual file stored in PostgreSQL. And this file is related to table foo. So what I said, every table in PostgreSQL has physical disk. So this is the file of table foo. All right. Tuple stored in table does not have any order. Like when you store tuples and rows in PostgreSQL, so it does not have any order. It can be stored in any order, because when you delete a tuple, it will mark deleted, and you insert the tuple, it will reclaim the space, vacuum, auto vacuum. So it's not in order. So it's just a tip. I will discuss it why I have told this thing. So the next. So when we want to see a data in a table, what will you do? Like suppose table is a book. When you want to see something in a book, what will you do? If you don't have an index, just leave it that you don't have an index at the end of the book. You just have a book and you want to see something in that book. You want to search something in the book. So you have to scan, you have to read the whole book again and start marking where you find the data. It's same with the table. It's same with the table. When you have to scan the whole table to search your data. So select a table row. So here is an example. I am row where ID is 5432. It should not be a sequential scan. Like explain, select name from bar and query plan. Here you can see it did a sequential scan on bar. Like mean it sequentially scan the whole table to get the data from the bar. And here I put the 5432. It just, what it does, gather parallel sequential. Just forget about the parallel right now. I'm not discussing here what is the parallel. So it's another topic for here. So it's a sequential scan on bar. Even it's again a sequential scan. And it's searching for the ID 5432. Like you have searching a word in the book and you are start searching from start of the book to the end of the book. So where this word is there. So it's expensive. It's really expensive to every time you want to search something, you start reading the whole book, you start sequentially scan your whole table. That's hard. So how it works when you try to select data from a table. Here I have created a table foo with ID and name, and I want to insert data, two rows, one with the value 1 and Alex. What it happens? Postgres has a column which is called a CTID. You can always select with CTID. It's already attached to the table. So you can select data from there. So when you insert a data like foo, 1 and Alex, 1 and Alex, and you can see 0 and 1. What is 0? 0 is the page number. In a table, physical file, it is divided in pages. So your table physical file is divided by default it's 8K of size, but it's default size, so I keep in that as a 8K. So 8K size of pages, and you can you can see its pages and tuple are stored like this. It's a page 0, page 1, page 2 and page n in a file. So when you select CTID, ID and name, you can see the 0 is the page number and 1 is the offset where actually the tuple is stored, right? So here I say 0, you can see 0 page number, 1 is this one, tuple ID. So tuple actually is an offset, but for the simplicity I said 1, you can see is a tuple 1. You can see LX, which color is, you can see the change the color that is related to this one. Okay, so how to select data from heap? So when you select the data, it will sequentially scan 1 and LX, it will see that it's 0 and 1, it will go there and extract the data for that. So it has the actual location of each and every tuple, okay, in the physical file. So need to scan every page. When we want to search LX, what we want to do? We want to scan each and every page of the file to search the LX. That's the problem. Tuple, what is the problem? The cost. Because it's a problem, because it's a slow process when you only want to select a one tuple and you want to scan the whole table. Here come the PostgreSQL indexes. Why indexes? Indexes are entry point for a table. You can see when entry point, why I am saying the entry point, like go to the back to the same example of book. You go to the end of the book, you can see the indexes, you can see a word in the book, you can see the page number of the book, and directly on the page number you can go to the page number and you can see that word. So that's the entry point on that book. So it's again the indexes, PostgreSQL indexes are entry point to that table. So you can read the data from the indexes and get the pointer from indexes, and you go to the heap and get actual data from there. Indexes used to locate the tuple in the table is the same. Indexes are used to locate tuples in actual table. Then indexes is a separate, like we already told you that each and every table has its own physical file. It's same for the indexes. Index has its own file. All right, because it also needs some space. When it's required a space, then we need to have some file for that. So here I just explain select name from bar where ID is 5432. You can see sequential scan on bar, and here is the cost. Just it's arbitrary number. It's not second, it's not millisecond, it's a number. You can compare that number. It's a smaller number, then it's faster, it's a bigger number, then it's slower. So it's arbitrary number, but its cost is. So you can see 5432, and I have created an index on that. Create index on bar, create index bar index on bar ID. And when I run the same statement, you can see bitmap heap scan on bar, and it use a bitmap index scan bar index, right? So its index is used. Here is not the sequential scan, and you see the cost. It's faster than the sequential scan. So I will explain you how it works, why it's faster than that. It's 40% faster than that, but it's just an example. So maybe you can get more. So Postgres standard way of create indexes, just go to the PostgreSQL site and you can see how to create an index. This is a bigger syntax for that. So I don't want to discuss each and every step to how to create an index, what kind of options are available. to create an index, but I will explain how it works here. So create an index IDX B3 on bar IG, and you see select rel file node from PG class rel name IDX tree. You can see rel file node 16425, and here again you can see this file. Similar you have for the table, you have a physical file for the indexes. You can see catalog table, you are selecting from the physical file. So creating an index based on a single column of table, like that start from the basics. You are creating an index on a single column of the table. Explain select name from bar where ID is equal to 543. You can see a simple single column index here. Here bar is a table and ID is also table and ID is a column. So when you create an index, a simple index, it locks the table. It locks from the deleting, updating, and it will lock that table. So that hurts. It's a performance constraint, because you don't want to block your update, deletes, insert when you are creating an index, because index is not high priority task. But high priority task is you don't want to lock and blocks your update and deletes, right? So Postgres has another way of doing that. It's called concurrently. Like you can see the time, it's in millisecond, you can see, but it will consume more time to create an index. But in that time you will able to update and delete it. So it will not lock your table. So you have a two option. One option, just create an index and your update, deletes will blocks. But if you don't, but it will work faster than that. But if you do that concurrently, it will slower. It's a slow process to create index, but it will not block your update and deletes. So it's your choice what you will do. So expression index. We already discussed that what is the simple index. So Postgres has a concept of expression index. Like you don't want to create an index on a simple column like ID, name. You have some queries which always use some kind of an expressions, like greater than something, less than something, +2, plus something. So expressions are used in your query most of the time. So why you are creating an index on the column? Why not create an index based on that expression? So you know you have an expression, same common kind of an expression. Like here an example, you have a query where you always select a data where name is in lowercase. So it's one option is I can create an index on name. But whenever I get the data, I have to run the lower, and that data will be get the data, invoke the lower process on that, and extract the data from the table. So why not I have to create an index which on that expression I am using mostly, in this case which is the lower. So here I have created an index expression on bar, and instead of writing name here, I just put the expression here. It can be any expression. I put it here at the most simplest expression here, like a function. We are calling a function here. All right. So it also gives you the cost, or you can see the index scan, or you can see here the lower index condition. Like here, it is using the filter. Here it is actually the index condition is lower name. If I have not used lower here, it will run the name on this and then put lower on that. So that's a slow process of using that. So I told you that we can use the expressions, but previous example I used the most simplest, like I've just run a lower function on a column and that. But it can be a complex expression. Like here, you can select strike from bar where a date time column is plus interval 2 days. It's a bit complex expression here. So one way is I just create a index on date time dt column, and after the indexes I will apply a filter on that, and that apply that expression on each and every row. So here I just created a index on that where dt plus interval 2 days, and this interval condition is used here. That is called expression index. So you have that option here. Postgres has one more option which is called a partial index. What is the partial index? Suppose you have millions of rows in your table, right? But most of the time your query, like you have a 10 million rows in a table, but mostly your query runs on 1 million of data, first 1 million, all right? And you are not running any queries or hardly running any queries which is 2 million, more than 1 million option, right? So why I am creating an index and wasting my space creating an index on whole 10 million rows? It's an option, just create an index on just 1 million of rows, because you are not running any queries more than 1 million. If somehow you are running a query which is greater than 1 million rows, then
not being seen on the live stream.
Oh, that's like, okay. So I lost. So there is a option that, like you have an example here. I create an index which is called idxfull on bar id. So I put where id is less than 1000 and name text this, and we run that query, right? And we have the same query here. So if I create an index on id is less than 1000, here I create an index on a table where there is no where class. Here we have a where class id is less than 1000. So you can see the size of the table here. Here the table size is 214 MB, 214 MB. Here the size is just 240 KB. So you have created an index which contain only rows less than 1000, right? So it with the size here, the size is only 240, and you have, when you created an index with on the whole table, it is 214 MB. So what happened? What happened when we query greater than id 1000? This index will not be used. That's simple. Then you have to scan your whole table. But you are not running most of your queries which is greater than 1000. So you are saving your space, all right? You are saving your space, but it hurts when query is greater than 1000. Your ID is greater than 1000. So it's trade off, but its answer is simple, the index won't select it. So Postgres has different kind of indexes. So we will discuss which kind of indexes we use at what circumstances. First, what is the B-tree index? By default, when you create an index in PostgreSQL, it's B-tree. You specify or not specify, it's B-tree. You can specify that we are creating an index, B-tree index, it will be a B-tree index. When you create an index without specifying anything, again it's a B-tree index, right? So spotted operator for that, when you have a condition less than, greater than, equal to, greater than, equal to, less than, so it works almost every kind of an operator, all right? So what is B-tree? Just go to the wiki page and just read that, because it's no time here to discuss the complete detail of B tree, how it works, but I will show you how B tree works in PostgreSQL. I have created an index IDX B tree on foo using B tree. So as there is a using word, so if I not use using B tree name, it will again create a B tree index. But I use using B tree, but for other indexes I have to use using for that. Like create index IDX B tree on foo using hash name. Hash is another type of indexes, but I will discuss this later. Explain, analyze, select static from foo where name is equal to text something. You can see the index scan is used, and index scan is used B tree on foo. That's it, and this index is used. The second one, the how it works actually. Sorry, I have created a table foo text and have many columns here. Like I have hundreds of column here. Like insert into foo values 1 Alex and other columns, insert to Bob and other columns. All right, I have selected select CTID static from foo CTID 0 1 Alex and other data. It will show the hundreds of column here. So 0 is the page number, 1 is the offset. All right, so whenever I want to select the Alex, I have to scan this whole table and want to select to the go to the that location. And when I created an index on that, and on name insert index have the key and the location of the tuple. Here we have a hundreds column and this CTID. When I create an index on the name column like this name Alex, it will store only the index column and the CTID. Like when you have a full page in the book, have many words on the page, but at the end of the index, what you have? The name and the page number. Here in the table we have all the columns and the CTID, but here in an index we have Alex and the CTID. We don't have any other columns, right? So we directly go there and get the Alex data. So here Bob, Alex, so we can directly search from here, go to there and select the data. So in some condition we are not going from here to there, and this we can go directly. I will discuss later in this slide. Like Alex, hash indexes. What is hash index? In B tree we are creating a B tree for that, but for the hash index we are creating a hash of that column and store that hash, and we will access that hash when required. So this is the limitation, or you can say it's not a limitation because it's implementation that hash index are used for the equality operators only. It's not for greater than, less than, because there is no concept of hash values to have a greater than and less than. It's exact equality operators. So it works on the equality operators. So when I created an index on a name, B trees was already there, and you can see I have used using hash name. So we have a two B tree. Sorry, it's hash. It's hash. Okay, was just typo here. So IDX hash and on using hash on name. Explain, analyze, select static from bar, where's this, and ID hash. IDX hash is used here. All right. The next one, the brin. Actually, I have told you that B tree works well on the equality operator, less than, greater than, less than, equal to, something, and hash is for the equality operator. But in my experience, B tree equality operator is much better than the hash equality operators. Even people are recommending that use the B tree even for the equality operators. This is BRIN is another interesting type of index in PostgreSQL. It's a block range index. When your data used when column have correlation with their physical location in the table, like date, when you inserting a data in sequential and it has a physical correlation with disk. What is the physical correlation of the disk? Like you are inserting data of 1st January, 2nd January, 3rd January, 4th, and in the sequence, and when we are storing that data, it's a sequential in the disk, right? So if this structure is there, like you are storing the serial number 1, 2, 3, 4, 5, 6, and it's sequential order, there is no unordered value there, so it's fit in BRIN index. And you already know your data. When you know your data, you can better choice what kind of an index you can use, right? So you are using, when you have a physical your data have a physical correlation with your disk, then you can use a BRIN index. So it is space optimized index. Why? You know, when in an index, in a B tree, in a hash, like in a B tree, what we are storing? We are storing the actual column of the data and the page number and the offset of that. We are storing the in an index. But here, what we are storing in the index? We are storing the page number, the minimum value of the column, and the maximum column of value of the column. Like in a page number 1, and we are storing date from 1st January to 31st January. That's it. We are not storing any more data. So space optimized. Because whenever I query that, I know my the date 1st January or 31st January will be on page number 1. And when I say page number 2, 1st February to 29th February, has that data. But if you don't have this kind of a data, this index will not be used. So it's your choice. You must know your data is physical correlation with the disk, that as it is you have the data. So it's interesting because it's only have a space optimized. So here I have created a BRIN index, and you can see the 7 normal index is used. You can see filter, remove, and time is 7397, and you can see BRIN index in 43 milliseconds. It's faster because this choice is really simple. Because when you say 21st January, it will go directly to the page number and get to your data. You can see the size, create index B tree, hash, BRIN, and you can see the BRIN index size in KB. It's very small, but it has its own limitation. Next one, this is some kind of a complex, there is 2 complex indexes are there. But normally we use B tree, hash, and BRIN. Now you have a GIN, which is generalized inverted index. Why would need that? GIN is the handle where need to index composite value. Like you have when you are want to create an index, you can create on single column, second, 2 column, 3 column, expression, partial, but there is some kind of limitation where your index is not full for your requirement. Like here, you have an example here. Like a bar is a table where is ID 1 column, JSON B column, date, you can see a date, and I have a data like this. What happens when I want a phone number which is 3333? How I can select that? How I can create an index for that? I can only normally index B tree, hash, and BRIN. I can create index on ID, name or DT. And here is the name. If I create a B tree on hash index or name, it will create an index on whole this JSONB column. So it's saying itself to create the whole column. So it's how I can say if I want to select the name is Alex. I cannot do that with normal indexes. So here is an example. What I will do, I will create a gin index on using gin name, and here when I select name is Alex, name in Alex, it will, you can see the timing 1079, and when we have used where it is used, this one, index condition is name, Alex is JSONB. It will select within the JSONB data and select your data for you, then it created an index, and it's speedy. You can see the time difference between 457 millisecond and 107, it's almost 60% faster than that. So it's not a normal index, right? I have selected a data from where name is name Alex. Actually, this is not greater than its range value. It's within the range. The next one is GIST, generalized search tree. It is tree structure access method. Actually, it is indexing framework used for indexing of complex data types. Like you have find a point within the box, use full text search, int array. You have this kind of data and you want to use a GIST, you can use that. It's a framework to use it. So the major question, when and where and how you use your, at where and what actually. The first question in B tree, when where you use a B tree index, use the index for most of the queries and different data types. It's normally used, people are using the B tree index. If you don't have any specific requirement, use B tree index. And hash used for, especially for equality operators. Brin for really large sequential lineup data size. You have a very large data size, millions of rows, but it's a sequentially lineup. Like I already told you that serial number, you have a serial number, you have a date which is incremental or it's decremental, but it's same process. Okay. So GIN used for documents and array, like I have already told you, and GIST used for full text search and finding geometrical values in the points and arrays, then you can use the GIST. So one more interesting thing is that it's index only scan. I told you that if I have a value in an index, right, I have data in a table and already data I have in the index, right? Like I have a, if I go to this example here, then you will no, sorry. Here, sorry. If you go to this example, you can see we have a data 0, 1, 1, Alex and hundreds of rows. We have a 2, 2 Bobs and hundreds of column and hundreds of column here. But we already have a data CT ID and name Alex is also here. So if my query is that is Alex in this table or not, like name is equal to Alex or not, one way is this, that I go to the Alex, find index in there, go to that table, scan the heap and see Alex is there or not. Normally we do that because we index is the pointer, we go to the actual value, see that value and return that value actually. But there are some queries where we only access the index data. We are not involving any other column. then why we are going to the table direct answer from the index? That's called index only scan. Like if you have an index on 4 columns and you are only querying that 4 column and your query does not involve any other column other than that, so it is faster than that. It will use index only scan. It will get the answer from the index. It's not going to the heap to get the answer. It's directly from the index. So it is called index only scan. So it's more faster than indexes, normal index. But you must know at what stage you need index only scan. So index is stored separately from tables main storage. Query need to scan both the index and heap. Normally index only scan only use when all columns in the query part of the index. Okay. In this case, Postgres fetches data directly from the index and it only index, not heap. So here is an example right now. I have created index, it's called index only scan, just index name, on ID and name. You can see there is ID, name, DT, another column, right? And bar, ID is greater than this. It is index scan. Why? Because I have a one column which is not part of the index. We have a one column which is not part of the index. We have two column, ID and name, part of that index. But DT in this query is not part of that index. So it will scan first the index, then get the pointer from there, go directly to the heap and get the data ID, name and DT. So it's two parts, one for the index and heap. It is also reading the index and the heap. And here index scan is using, right? And other query where ID and name from bar, where ID is greater than something and ID greater than less than. Here no column from heap is accessed. All the columns are present in the index, like ID, name, ID and name. No column other than index. So index only scan is used here, right? So it's faster than the index scan, but it's matter of choice. If you have, it depends on your queries and your index creation. But people likes to have this kind of indexes to manage your queries and that it fits on the index only scan. Duplicate. There is some kind of a queries, and I have some example of queries where from the catalogs you get the information that your index, you are using the proper indexes and you have a proper garbage collector for that collect the garbage, because it happens when you create an index and you forget about that index and you create another index sometime, and sometime you created another index and you forget about that, how many indexes you have on the table. So you must run some kind of queries on your catalog to search what kind of duplicate index on that column and that table I have. So this is the query. Interesting query that I have it's from the catalog table. You can see PG index this one in key, and you can see bar has a 2 B-tree index on a bar table has a similar index 2 with the B-tree. 2 similar B-tree index bar table have. So if you have hundreds of table, hundreds of indexes, you run that query, you can get that which table and which table has a similar index which is a duplicate, because you can drop some kind of an indexes, because you don't need same index on same table. Okay. So here is another query that you will see that what kind of data type is supported for which index, right? Every index does not support every operator, right? So here is the query. You can write this query change this gin, gist, b-tree, hash, it will give you the operator name, that which kind of operator can be used for this index. So you know that. So here is the unused index. Some you have index and you don't know you have used it or not. Like people created an index, or after 1 month they say, oh, I am not using that index. How I can get that information? So here is the query where you get the unused index that is hardly used. Like you can see, this index is never used, 0, 0, and this index is used only 6 times, it's a 4 times. So you can get the query that my index is used since last 1 month or 2 months or 3 months, that it is never used. That means we don't need that index. Drop that index. Otherwise, tune your query to use that index. It's question time.
Doing a query with a function, expression, and your index doesn't have the expression, is it used at all?
Yeah, it will. He is asking that your index does not have expression index, and you are using the function. Does index use? Index will be used, but it will get the data on that column and then apply that function on that.
You mentioned in the presentation that hash indexes are slower than B-tree, which is kind of awkward because hash has a big O of a constant. Do you know why is that?
Yeah, he is asking that hash is. I told in the presentation that hash is not as good as B-tree, but normally in journal hash is better in equality operator.
Data structure.
Yeah, in data structure. But that is a problem that in practical I have seen, and people are also mentioning that B-tree works better than hash in, maybe it's a kind of an implementation. I'm just talking about in Postgres implementation. It's practical experience mine and other people. I'm just reading around that people are also experienced that B-tree works better in equality operator.
I think Postgres 12, I think it's been pretty much fixed.
Okay, he's saying that
I can't guarantee, I haven't done my own performance.
as performance
There's
that
been a lot of improvements.
yeah, a lot of improvement have been
All
done.
the wall support. Before, hash couldn't get replicated either. But now hash indexes can get replicated, and now that people are actually using it, I think someone focused on the performance, and I think at least for some use cases, hash indexes make sense over B-trees now.
Yep. He's also saying that in PostgreSQL 12, it's improving.
It might have been in 11, it might have been in 12.
12.
I forget which.
So it's improving.
Was it 10?
I don't think to 10, not 10, but maybe it's improving. It's matter. So it's improving. So, but it's not the data structure. It's in PostgreSQL. Any more question?
How many indexes on the table you would say would be too many, where like you should think like I shouldn't create anymore?
It's all your choice actually. Oh, sorry, always. Is how many maximum index is we can create? There is no limit actually, and in practical,
You know, in practical sense, performance might degrade on inserts and something.
yes, actually, it depends on your queries and your table sizes, and you have to analyze that. You don't want to create duplicate indexes on that. I cannot say that if you have a small table, you cannot create hundreds of index on that. You can, but it's matter you have to analyze that. You can see that how many indexes are used. Like I have give you the query. You have to run some catalog queries on that. So how many indexes are used? Remove unused indexes from there. Analyze your queries. What kind of column you are using in the index? Try to be fit in your index only scan. Then use proper indexes and remove all unused index from there.
So again, that green
Yeah, in the indexes it is. But he is saying that when the index is storing the page number, it's sequentially scanning there because the index has a less information. It does not have a complete table. It will go sequentially on that it will get the, because when you go to the indexes, you have the pointer of that, so you could direct it to the table.
Does an index only scan work if the columns are in different indexes?
It is, because it will not go he said if the index in a different indexes, index and scan will be used, because it will use the index scan. It will not, if each index, it will not go to the heap, because the data is already in an index. Data is already in the index. It does not need to go to the heap, because already data has its own data structure. I'm just waiting.
2 more minutes. Any more questions? All right. Well, thanks.